Okay, so let's do our first calorimetry example problem. So here's another typical type problem you will run across. So we have a 53.0 gram piece of quartz that is at 100 degrees C. And we're going to drop it into 100 milliliters of water at 15 degrees C. So we want to figure out the final temperature, assuming that no heat is lost to the surroundings. And we're given a little bit of information, which is the specific heat capacity of water, 4.184 joules per gram degree C, the specific heat capacity of quartz, which is 0.742 joules per gram degree C, and the density of water we can assume is 1 gram per milliliter. Okay, so how do we approach this? All right, so we're starting with two materials at two different temperatures. And one of the ways that I like to think about this is by relating the heat of the hot thing to the heat of the cold thing. So remember, the heat is going to leave the hot thing and enter the cold thing. And so we could say that the water is the cold and our piece of quartz at 100 degrees C is hot. Okay, so let's relate those two heats. Okay, so we could say Q hot is equal to Q cold. Okay, now remember, in a calorimetry experiment, we need to make them equal in magnitude but opposite sign. So I'm going to put the negative sign in front of the hot thing. So heat is going to leave the hot thing and enter the cold thing. Okay, so this is an assumed positive. I'll put it in there, but we don't have to. Okay, all right, so there is our relationship. Now, the other thing that we are going to remember is this general equation for heat, which is Q is equal to the mass in grams times the specific heat times delta T, okay? And we're going to write one of these equations for each one of these quantities, okay? And we have most of the information. We're going to end up solving for T final, okay? So also remember that delta T is equal to T final minus T initial, okay? All right, so let's go ahead and do that. Let's write out the hot thing first, okay? I think that I will go to the next slide to start doing that. So let's do that. Okay, so just to write down a few things here that we already had. So we had negative Q for the hot thing, and we had Q for the is equal to the Q for the cold thing with the opposite sign. Okay, we had a 100 degrees C piece of quartz. Okay, and it was 53.0 grams, and its heat capacity is 0.742 joules per gram degree C. Okay, and then we also had 100 milliliters of water, and we had a heat capacity for water of 4.184 joules per gram degree C, and we also had an initial temperature of 15 degrees C for the water. Okay, so that's the important information that we need to keep track of in this problem. Okay, so let's go ahead and label these just a little bit differently. Okay, so negative Q, this is going to be for quartz, is equal to Q for water. Okay. All right. So now let's just start filling some of these things in. Now, in these problems, it's also really useful to expand delta T into T final minus T initial. So I'm going to go ahead and do that. Don't just solve for delta T. All right. So let's start plugging in. So we have a negative sign. Okay. We have a 53 gram piece of quartz. Okay. We have its heat capacity, 0.742 joules per gram degree C. Okay. So this is going to be delta T. I'm going to write that up there, but I'm actually going to write T final, which we do not know, minus 100 degrees C. Okay. And that's going to be equal to an expression for water that we're going to put in there, okay? So we have 100 milliliters of water, and we know the density of water is 1 gram per milliliter, okay? So I'm going to write this in a little bit different color up here. So 100 milliliters of water, 1 milliliter gives 1 gram, okay? So that's 100 grams of water. All right, so let's go ahead and write that in there. So 100 grams, all right, and the heat capacity for water, 4.184 joules per gram degree C, okay? And then finally, we're going to do the same thing, T final minus T initial. T final minus 15 degrees C, which is our initial temperature for water. Okay, so now we're ready to do a little bit of math, okay? So let's look at this again, just make sure we understand what we're doing. So here's our mass of our quartz, its heat capacity, okay? So this is MCS, and this is delta T right there. Here we also have MCS delta T expanded, okay? All right, and so let's go ahead and multiply 53 times the specific heat, okay? So we're going to end up with negative 39.326 joules per degree C, okay? That's after we do that multiplication. And then we're still going to have T final minus 100 degrees C, okay? Let's go ahead and multiply the mass of our water times its specific heat, and we're going to get 418.4 joules per gram degree C, okay? And we also still have this delta T. We have the initial temperature, but we don't have the final temperature. Okay, let's go ahead and divide out this. So 418.4 joules per gram degree C, okay? Divide this, 418.4 joules per gram, sorry, no gram there. The grams went away. All right. So let's leave that. So we have degrees, so it's joules per degree C, okay? And let's do some more math here. Okay, so we're going to divide 39.326 divided by 418, and we are going to end up with, and remembering our negative sign there too, we're going to end up with negative 0.09399, okay, and it's unitless now, so see how we canceled all those out. We end up with TF minus 100 degrees C, and that's going to be equal to TF minus 15 degrees C. All right, now a little bit more math. We've got to distribute this, okay, so now we have negative 0.09399 TF, okay, and then now we're going to multiply this by 100 degrees C, and then notice we have negative times negative, so we're going to end up with a positive, okay, and when we do that we're going to end up with 9.399 degrees C, okay, and that's going to be equal to TF minus 15 degrees C. Okay, now I'm going to go to the next slide, and then I'm going to write down what we have right here in this line, and then we'll continue solving it. Okay, so going with what we had before, negative 0.09399 times TF plus 9.399 degrees C is equal to TF minus 15 degrees C. Okay? All right, so let's go ahead and add this little TF to the other side. Okay? So we'll collect that. So now we're going to end up with, so this is plus 0.09399 TF. Okay, so now we're going to end up with 9.399 degrees C is equal to because remember this is a 1.09399 times TF minus 15 degrees C. Okay, adding 15 degrees C to both sides. Now we're going to end up with 24.399 degrees C is going to be equal to 1.09399 TF. Okay. Final step, divide this out, 1.09399, divide both sides. Okay, and now we end up with a final temperature of 22.3 degrees C. We need 3 significant figures. Our original problem had 3 significant figures. The other thing that you should think about is we dropped a hot piece of quartz into 15-degree water, and at the end the water temperature increased to 22.3 degrees C. So does this make sense? And I would say yes. So hot flowed out of that hot quartz into our cold water and raised the temperature of our water.